Hi, this is Sebastian Kruse, and in this video I want to present to you our tool Metacrate. In brevity, Metacrate can be thought of as a database for structural metadata, and it is supposed to support metadata-driven applications such as data exploration, database reverse engineering, or data discovery. And in this video, I want to show you how we can use Metacrate for a data analysis. To see what it means and why it is important, let's get right into it. So suppose you want to take up a project around an unknown dataset, for instance writing an application or conducting a data science project. Independent of what nice contents your dataset has, technically it is always a bunch of files, and if there is no documentation of the dataset, then it might be really hard to understand and work with the dataset. For instance, in this video I have obtained an example dataset called BioSQLSP, and if we start eyeballing it, then you see it's just a bunch of CSV files. And if we look into one of the CSV files, it's even a large file, so we have to wait a bit until it is loaded. Yeah, well then we just see some attributes, like 5 attributes in this case, and it's not really clear what is going on here. For instance, this first attribute, is that a primary key of the table? And if so, how can we use that primary key to join this table with other tables? And how can we actually answer these questions? So should we now look at all these tables here manually? And what if our data set doesn't have only like 28 tables, but let's say hundreds or even thousands of tables? You see, working with a new data set can be a challenging task, and we refer to the activities needed to get started with an unknown data set as data analysis. And that essentially means that we have to inspect the data to reconstruct not only a technical schema for the data set, but also to get an understanding of its contents so that users can actually start to work with it. And the first step to get on top of this task is data profiling. Data profiling is defined as the process of creating what we call structural metadata. That can be summaries of the data, such as histograms or other statistics, and structural properties, such as which columns combined in a table make up a key candidate. To do the data profiling, we have developed the tool Metacrate, which aggregates quite a lot of diverse, efficient, and scalable profiling algorithms. The problem is, if we run all these algorithms, then, as I show you here, we again just get a bunch of files. In fact, here we get one file for each table and each type of data profile that we extract. For instance, here we have a bunch of statistics on the different columns of one table, but you see again it's just a technical file and it's hard to read, and actually we're still quite a few steps away from an actual data analysis. For instance, we need to detect the interesting data profiles among all these results that we just got from Metacrate, and also we need to combine different types of structural metadata to really derive rich insights, and that is exactly what Metacrate can do for you. Before we get started with our data analysis, let me say a few words about Metacrate. Metacrate is an open source project and it is available on GitHub. And we aggregate the link to this GitHub repository as well as other resources on our projects page at the far bottom. And either you are already on that project page while seeing this video, or you should be able to find a link to it in the video description. And let us go to the GitHub README and have a look at this figure here, which explains the principal components of Metacrate. So essentially, Metacrate is a backend system similar to a relational database, for instance. And at first, it lets you store and organize your data profiles on various storage backends, and specifically, you can import your data profiles that you just profiled with Metacrate directly into Metacrate, so there is a seamless integration of these two tools. Then furthermore, we offer an analytics layer, and this analytics layer lets you query your structural metadata, and also it comes with a bunch of richer analytics functions, and both the queries and the analytics functions are integrated so you can combine them while working with Metacrate. And although I said that Metacrate is a backend system primarily, we also offer integration with Jupyter Notebooks, which gives you a very basic client to work with Metacrate. And it can be seen as a substitute for the administration tools that you get, for instance, with Postgres or with MySQL. And this integration essentially allows you to interactively manage and query your Metacrate instances. And additionally, it comes with a bunch of dedicated visualizations, for instance, for data analysis. And in the following, I will especially show you how we can use the Jupyter client to perform our data analysis of the dataset that we have just seen. That being said, if you want to play with Metacrate yourself, you can also find installation notes as well as a few words on how to get started with Metacrate on our GitHub page. Okay, enough with the preliminaries. Now let's finally start our data analysis. And for that purpose, I have created a Jupyter notebook, and you can download this and other notebooks on our webpage. So this is basically the starting screen of Jupyter, and here we see a bunch of notebook files, and specifically now I'm opening the data anamnesis notebook. And yeah, a Metacrate Jupyter notebook usually starts with a bit of boilerplate that is just necessary to load the Metacrate binaries into Jupyter. And once that is done, here is some configuration. So here just for convenience, moved all the configuration of what we want to profile into a central place. But the interesting part starts here. So when we want to work with Metacrate, the very first thing that we have to do is to create a new Metacrate instance. And in this case, we are choosing the SQLite storage backend. And once I have created or executed this command, you see now we have here a database file. So this is the SQLite storage backend on which all further actions will happen eventually. So once we have created our Metacrate instance, the very first thing that we have to do with it is to import a schema. And to import a schema, we have the so-called import object, which offers a bunch of importing functions, specifically here the create schema from CSV files function. So let me execute it. And what it basically does, it goes over all the CSV files that I've just shown to you and looks at which files are there in the first place, so which tables do we have and how many columns are in each of these files. And if we are happy enough to have an SQL file, then we can also give it to the importer, so it will use the SQL file then to load column names for the different columns in our data set. Remember that our CSV files did not have column headers. In this case, we are indeed happy enough to have an SQL file. And you can see it's basically just a regular production SQL file that we have parsed here. And the schema is very important because for the following steps, it basically gives us the context to attach all our metadata to. And to now load actual metadata, we have again the import object and a bunch of other import functions like import metanom statistics or import metanom dependencies. And if I execute these functions, they will go over the metanom files that I've just shown to you, parse them, and load them into our newly created Metacrate instance. And in the course of our data analysis, we also need samples of our table, which we also regard as a data profile. However, this is a profiling option or type of data profile that is not offered by Metanom. So Metacrate compensates for this by offering this profiling object, which gives you a bunch of simple profiling tasks. And note that this task only needs to know the schema that we want to profile, because Metacrate already knows which tables belong to the schema, where they are stored, and how we can parse the certain CSV files that make up the tables of the schema. Last but not least, here we have a simple query which shows us the contents of Metacrate, so basically all the metadata that we have just loaded into it. And the important thing to note is that Metacrate organizes metadata in so-called constraint collections. And the constraint collection is just a set of data profiles of the same type, and it has a bunch of features. For instance, it has an ID and possibly also a user-specified ID that helps us to retrieve profile collections and, for instance, query them and so on. Also, each constraint collection has a type as well as a scope, which basically declares the parts of the schema that are addressed by this constraint collection. And we can use these features to declaratively retrieve constraint collections later on. So these are basically the contents now that we will use to perform our further data analysis. Now let's start with the analytics part. For starters, let's start with a simple query. So at first one might want to get an overview of data set and specifically its extent. So we are doing a very first query in which we just analyze for each table how many columns and how many rows or tuples it has, and display this in a scatter chart. And this is easily achieved by a query which just loads the number of columns for each table, then gets a constraint collection that contains the number of tuples for each table, and then we join those two and finally plug them into a scatter chart. If we execute this query, then here indeed we get such a scatter chart, and actually we see a very typical distribution of tables. So usually we see that we have only few tables which have relatively many columns, but only rather few instances. So here, for instance, we have this bioentry table with 9 columns and 184,000 tuples. And on the other hand, we have a few tables which have only few columns, but very many instances or tuples. And typically the tables here are joined tables, while the tables here usually tend to be central instances of a schema. Right, so this gives us at first an idea of which amounts of data we face here and which tables we have. So now in the next step, one might need to reconstruct the schema. As I said, for instance, we might want to know which are the primary keys in a data set and which are the foreign keys in a data set. And data profiling can help us here. For instance, by finding so-called unique column combinations. And the unique column combination is basically a set of columns in a table which together uniquely identify every tuple in a table. However, usually we find many such unique column combinations and every one is a key candidate, but it's not clear which one should be the primary key of that table. So to find out, here in Metacrate's analytics library, we have a machine learning model that takes the unique column combinations of Metacrate, along with other kinds of data profiles, for instance, column statistics and text statistics. And yeah, we can use that to infer the primary keys, or basically predict which key candidates are the real primary keys in a data set, and then store this in a new constraint collection. And I will do this now, and I will also output the results here. So here you can just see basically the parameters of our model. So these were trained earlier. And here we get a list of predicted primary keys for our tables. So you see they seem to make sense mostly, especially because we see the word ID every now and then. We can do a very similar approach for finding the foreign keys of a data set. Only here we are not using the unique column combinations as our base instances, but so-called inclusion dependencies. And an inclusion dependency describes that all values from one set of columns can be also found in another set of columns. And these are basically foreign key candidates, but again, we need another or other types of data profiles to make predictions of which are really the foreign keys. And again, we have a machine learning model for that, and again store this in a constraint collection, and also output this result in this query here. And yeah, basically here you can see the proposed foreign keys. I have to say at this point they are not 100% correct, so usually it is always necessary that a human user then goes over them and corrects them or specifies missing foreign keys. But in this case we don't need to do this because, as I said, we have this SQL file here, and this SQL file also happens to specify both primary keys as well as foreign keys. Not quite sure where they are. Here they are. And as part of Metacrate's import library, we have possibilities to import primary key and foreign key definitions from SQL files. So instead of manually correcting them, now I just use this import function, and what it basically gives us in the end is new constraint collections. So you see here we have our automatically classified primary and foreign keys, and here we also have the ones that we just loaded from the SQL file. So now we can continue working with them. As I said in the beginning, in data analysis, we are not only interested in reconstructing the technical schema of a dataset, but we are also interested in building an understanding of the dataset so that users can actually formulate queries or understand what the tables and the data in it are about. And there are several ways to do this described in literature, and here I want to show you two basically supports in understanding a data set and how you can realize them with Metacrate. And the first thing I want to look at with you is the so-called table importance. So basically we have a bunch of tables and we want to know how important these tables are. And if we find the important tables, then we can specifically have a look at them first. So usually they are central instances in the domain of the data set. And once we've understood them, then we can often understand other tables more easily because they are, for instance, join tables or because they are kind of dimension tables for these instance tables. And the method that we implement here is based on interpreting the schema as a graph. So what does this mean? So here I have a small query in which I just load the foreign keys from our SQL file and put them into a directed graph visualization, and out comes the graph. And in this graph basically we have each table, like this one here, as a vertex, and the edges between the tables are join relationships, specifically foreign key relationships. And the method that we are using here interprets the schema, as I said, as a graph and uses the links between the tables to infer which tables are important, similar to a page rank. And this is part of Metacrate's analytics library, so you don't need to code a query by hand now that implements a page rank, but rather you can just use this table importance object and execute this and directly store the table importance results in a constraint collection. And then we just repeat our query that creates this directed graph, but here we are also loading the table importances right there and use them to describe the nodes in our visualization. And then we get a slightly altered graph in which presumably important tables are depicted larger than presumably unimportant tables. Like for instance, ontology is probably unimportant, so we should not look at it, but bioentry or comment are rather large, or sec feature, so it would be recommended to look at those tables at first. Now finally we want to show you a second conceptualization aid, namely the clustering of tables and how you can do that with Metacrate. And the very first thing that we need to do when we want to cluster our tables in a schema, we need a similarity measure. And there is a specific similarity measure already implemented in Metacrate's analytics library. and you can get this over the table similarity object here and feed it with various kinds of data profiles, for instance the foreign keys and how many tuples are in each table and so on. And out comes a bunch of new data profiles that we can then store in a new constraint collection. So we do this, and now we basically have the similarity measure. By the way, I should say how that actually works. The similarity measure is again based on the topology of the schema graph, and it basically qualifies how strongly two tables are bonded via foreign keys. And now we can use the similarity measure to perform our actual clustering. So again, this is something that is implemented in Metacrate's analytics library, and here we specifically use the k-weighted central algorithm. And what it does is it does not only take into account how similar tables are, but also how important tables are. This is because important tables are favored to get their own clusters, especially to be the center of the cluster. So here we execute this k-weighted center algorithm with a value of k equals 4. So in this case we want 4 clusters, and again store it in a constraint collection. Now we have these two new assets, namely the clustering and the similarities, and we can use that to build new visualizations to get deeper insights in our data set. So the first obvious thing that we can do is to color the graph, the schema graph that I have shown to you before, so that tables of the same cluster get the same color. And to do this, we just again extend our schema graph query. And here we not only load the importances of the tables, but also their cluster assignment, join those two, and these eventually make up our new vertices. And yeah, then we just put them into our plot directed graph function again. And then we get a new schema graph that is now colored. So you can see, for instance, this bio entry now seems to be the center of a cluster because it is an important table, and apparently these other tables like bio entry, qualifier value, or bio database are somewhat strongly related to this bio entry table. So it might make sense to at first get a deeper understanding and to look inside of this bio entry table. And once we have understood all the concepts of this bio entry table, it might be easier to understand what these other tables mean. And I would also like to propose a second way to visualize this table clustering, and that is in combination with table similarities to find out how strongly these clusters are actually bonded. And for that purpose, here we have a bit more complex query, but what it does is actually just combines the similarities again with the clustering and creates tiles, and these tiles are then just displayed in a grid. So here we also load rows and columns to bring the different tiles into order so that our clusters appear together. And out comes such a matrix, where again each tile is a pair of tables, like here for instance, and if the opacity of this tile is large, then these tables have a high similarity, as here is the case for this bioentry dbx ref table and the bioentry table. And basically it gives you a feeling of how strongly or how coherent these clusters are. So for instance, obviously here is a table biodatabase which is not strongly related to any other table. So we might need to refine our k value and run the clustering again. And apart from that, it also shows us how two clusters are best connected. So for instance, here we have two ways to connect the green and the violet cluster, either by joining dbxref and bioentry dbxref, or by joining bioentry reference and reference. And apparently this link here is the stronger, so if we need to have a join path between a table from this green cluster to this violet cluster, then this might be the better way to do the joining. Yeah, so this concludes the small overview of how you can do a data analysis with Metacrate. And as I said, if you want to play around with Metacrate yourself, you can visit our project page, and at the lower part you will find resources, in particular also example notebooks for Metacrate. This will give you way to a new GitHub repository, and there you can get an extended version of the state analysis that I just shown to you. And you can also see how you can use Metacrate, for instance, for data cleaning or for data discovery. And with that, I thank you for your attention, and I hope you have fun with the tool.